I'm going to write something like this. This is sort of the empirical measure associated with the data points. It's not, so the empirical measure, I mean, you can define something like that, 1 over n, which is 1 over n times this. This is the probability measure. This is oftentimes called the empirical measure. So, empirical. So if you have taken 200B with me, you remember this measure is, for example, sufficient statistic for IID data. So this just counts how many of the data points are in set A, and then divide by the total number. So this is a probability distribution on the whole space. But it's like discrete values. So in the univariate case, it's in one-to-one correspondence with the CDF, for example. But this sort of contains all the information in the data except the order of the data. So you lose that, but that's sort of not necessary. If you have IID data, that information is not useful for estimation. And this is the thing that I've defined here is for simplicity, this is the counting measure. So without dividing by n. So if I define this, so if I have a partition, so my estimator would have these partition cells, let's say. Okay, so these are disjoint sets. So if you recall, okay, you have to go a lot. Yeah, unfortunately. So these are the partition cells. So this, for example, is AN1. This is AN2. This is AN3, AN4. You can just like number them any way you want. Okay. And then for any x, I'm going to write, so if this is my x, I'm going to write ANX for the cell that contains this point. So for example, if this is AN5, in this particular case, it would be AN5. Okay, so ANX is the cell of the partition that contains X. It's one of these things, and the cells need not be cubic, but it's easy to visualize. So this result is very general. They can have in any form. Okay, so we have this partition of the space. And so what do we do? I'm going to write, so estimator, the estimator that we have is going to be like this. Okay, I'm going to simplify, write it like that, Wi xi from 1 to n, yi, and then wix. I can write it as 1 if xi belongs to a and x. Okay, I'm going to count xi if xi belongs to that cell. That gets a weight. And then I have to divide by the total number. I'm going to call this snx, where snx is just nu n applied to nax. So if you think about this, this is the cell that contains x. And so this counts how many data points there are. And each one gets a weight 1. So this is just averaging over those data points. Okay. So this is true if this guy is, so let me do this here. If this is, so let's define this like that. Snx is bigger than 0, and 0 otherwise. Okay, so if Snx is 0, it means that there are no data points in there. So we define it like that. So these are sub-probability weights in the sense that summation Wix is always less than or equal to 1. If there is one data point in there in the cell, it would be always 1. If it's empty, we define it to be 0. So so this satisfies the boundedness condition. This was one of the assumptions, like the second assumption. D equal 1. And then these are non-negative, obviously. So now to the tricky part. The first thing that we want to do is to like establish, let's say, the variance condition. And roughly speaking, so the variance is sort of, you want to say that this, when I apply it to the random x, the expectation sort of converges to 0. So let's go back up. That's this condition that we have here. The L1 means the expectation goes to 0. And so again, I'm going to do, so verify this. What I'm going to do is I'm going to apply it to a fixed x first. So if I apply it to a fixed x, what do we get? So we get summation wix squared. You can see their average. So what I get is this squared comes out, right? And then I get this. 1 when I square it just remains there. And it would be like this if I'm going to put a 1 SNX here. Otherwise, the entire thing would be 0. So 1 SNX bigger than 0. Okay, so that's what happens. So when I square it, the numerator remains the same. This gets squared, comes out. So I have that situation there. Right. Is that good? So what is the next step? Sorry? Yeah, we can apply expectation. So what would happen if I all right, so there's this piece here which is also dependent on x, y up to xn. So these are random as well. And this is also random. So here's where I have to cheat. It's a little bit tricky, but the idea is rather simple. So maybe you guys can think about it, tell me how to do it. There's a nice way of doing it, and there's a hard way of doing it. So let me first do something else. So what we have to do is so there is something else that we can do. Let me try to do this first. I can do rather simplify it. Let me first simplify it like this. I'm going to write it instead of this. I'm going to write it. This is going to be a little bit tricky. I'm going to write it as Wix 1 SNX bigger than 0 divided by SNX. This is a little bit cleaner. I should have done this from the start. This is saying that if this is bigger than 0, right, and then I can just drop this. So let's see if this works. So if SNX is bigger than 0, we have is this correct? This is not correct. Okay. Let's do this. This was not correct. this should be correct. So if I sum them, right, square, I would get what I had there, Snx bigger than 0 divided by Snx. So this was fine. I'm going to simplify at this point, Anx. So this is just nu n, Anx, right? This is squared. So this was the previous formula, and this is just the way I've defined it, Snx, okay? So this is just 1. So this is really a simple idea. It's just that the average, when I take the average, so you get 1 over, this is the how many elements are in that cell. And the variance goes like 1 over that. That's basically the idea. So it's just that this quantity is random, the number of points that are in the cell. So you know that when you take the average of a bunch of points with weights that are, so if you have, so each one has this weight. So the sum is 1, and then the square would be 1 over this. Is it good so far? So this is the first step. The next step is the tricky part because we have to, so if you recall, there is a bounding set that I have to bound because these partition cells could go on forever, right? So we have partitioned the whole space. If you want to count how many they are, they're infinite. So what we do is we put a bounding set, could be like something like that. So this is B. So I'm going to work on B, and then in the end, I can increase B to cover all the mass of the distribution, like most of the mass of the distribution. So basically, you truncate the support of the distribution of X to some B. That's the plan. So what we're going to do is, I want this expectation. So this would be, I'm going to multiply by, let me do this on the other side. So the expectation, Wix. I'm going to multiply it by the 1b, or the indicator that X is in B, plus the indicator that X is in B complement, okay? So that's so far, we haven't done anything. So when I multiply this out, over this part, I'm going to bound things properly. Over this part, I'm just going to bound this by 1. Okay. So if I bound this by 1 over this, expectation goes in. Apply to the indicator, I get the probability. So what I'm going to get is expectation Wi squared X, indicator XP, right, plus probability, this is an inequality, X in B complement. Okay, this is the part that I can make as small as I wish by making big enough. Are we good? Okay, so the next part of the trick, okay, this also gets a little bit tricky. So if X is, so here X is in B. Okay, if X is in B, I have defined this. So let's define it. What I want to define is, let's J be the set of all J, all the data points such that, or sorry, all the, not the data points, all the partition cells such that they intersect with B. Okay, all these, all the cells that are like have some sort of part in B. Okay, so the set of all cells that have a non-empty intersection with B. So if X is in B, then it's covered by these sets. So then X belongs to A and J for some of these. So then it means that, in other words, X is in B is a subset of the union J in J. X is in NJ. Okay. So because these sets, the union of these covers B, if X is in B, then it has to belong to one of these guys. Okay, so it means that this event is a subset of the union of these. Okay. Yeah. Where did I have? So A sub n, so A sub n x is different than n A n j. I haven't used A and J here. What do you mean by? So A sub n x is the cell of the partition that contains. So this would be one of these, depending on where x falls into. Okay, so this is, when I apply it with random x, it's going to be a random quantity. This A and J, you can just mentally remove n. It's just A1, A2, A3. These are fixed partition cells. Right, so what I'm trying to say here is that if x is in, so imagine a very simple setup. I have like cells like this. And let's say my bounding, but the bounding cell could be anything. Like could be like this. Okay, B could be this. I just care about all the partition cells that are like intersecting with this. So this is going to be covered. All these cells that have a non-empty intersection, and then if there are other cells outside, these we don't care about. Okay, so the red ones are all the, so the J sort of indices all these red ones, they intersect. And so if X is in B, it has to be, that because this covers the B, it has to be in one of these red things. So it means that it belongs to this union. So what this means is that if you think about the indicator is going to be bounded below by this guy. So if you have like a union relation, then the indicator is like this. Does that make sense? So this says, this is gonna, if this is 1, it's in one of them, so one of them would be 1. So this would be 1 less than 1. If this is 0, then this is obviously true. Okay. So you have this, so we can sort of replace, so this one, I'm going to call this, let's say, call this, should we call it like, I don't know, I1. So I1 is bounded by, I'm going to plug in this upper bound for the, plug this in here and then pull the sum out. So you get, and these should be capital X here at this point. What I would get is some J in J, expectation, I from 1 to n. So here I'm going to bound this by that. So this is just this, right? So what I'm going to get is, if you think about it, you'd get 1 Snx bigger than 0 divided by Snx, and then times indicator X is in A and J. Okay. So we plugged in the formula that we have for the sum. And so we first use this for this, and then I'm going to replace this with that, and then pull the sum out. Okay. So let's look at this, see if it makes sense. Does it make sense? This is just the summation. I just have this here. This is just summation wi and or wi squared x right from 1 to n. And I just plugged in 1 xp. So now the interesting thing is that because x is in a and j, so if x is in nj, then this just means that a and x is just a and j, right? So s and x, which was nu n, the number of points in a and x is just the number of points in a and j. Okay, so we got rid of so the trick was like get rid of the randomness here. Okay, so on this indicator set, I know which cell it is, and this is just how many points there are in that cell. So what I'm going to get is summation j and j, expectation 1 n a and j bigger than 0 divided by nu n a and j, right? And then the indicator transfer. Make it smaller. Okay. Okay. So this is good so far. Okay. Now, is this clear? So, sort of. Now, at this point, there is some interesting things happening here. So this is how many of the training sets are in this cell. So this part only depends on the training. This part only depends on the test. What can we do here? Yeah, we can just get a product. What I'm going to get is split it into 2 parts that are actually equal by independence, right? So j in j, expectation a and j bigger than 0, nu n and a j, times the expectation of this, right? This is by independence of training and test. So this would be probability of x is in a and j. And I forgot if I introduced the notation, but the distribution of x we represent as mu. So this is nothing but, by definition, just mu of a and j. Okay. So what we get is summation j from j expectation a and j bigger than 0, mu n a and j, and then mu a. And this is just deterministic. This is the under the population distribution. Okay, the only thing that remains is this. So what is the distribution of nu and a and j? If you recall, this is just summation I from 1 to n. How many basically xi's are in a and j? Binomial, yeah. So binomial with probability n and with number of trials n, how many? Mu of a and j, yeah. So the probability is just basically the chance that each one of them is in there. So it's just a binomial with n and mu a and j. So if you recall, all right, I haven't posted the homework yet, but something very similar happened when we did the simple example, warm-up example. So you have a binomial. So basically, the idea is that if I have a binomial, so lemma, which you're going to prove, if I have a binomial random variable, and then look at the expectation of 1, b bigger than 0, divided by b. I need one bigger, I need this because division by 0 is problematic. But let's say when b is bigger than 0, this is 1 over b. If b is 0, I'm going to define it as 0. Okay, the first thing that you can do is, it's not hard to see that this function you can bound by 2 over 1 plus b. If b is 0, this side would be 0, this would be 2. If b is 1, this is 1, this is 1. And then from onwards, so this is always a. So this is a simple thing. The only thing that you have to worry about is figuring out what the expectation of this is. And this, I think, is already an exercise in the notes that are posted. But you're going to prove that this is bounded by, this is not easy to control from above. It's easy to do from below using the Jensen's inequality. But if you want to get an upper bound, you have to do some work. But you can imagine it's close to just replacing b with its expectation, but it would be like something like this. Okay, that's the lemma that you're going to prove. I'm not wrong. So this is like a side lemma. Okay. So you also needed something like this for the warm-up example that I did. So this thing is just going to be an application of this, right? So it's a binomial. I'm taking expectation of 1 over inverse, basically, of a binomial. And so it would be, back to the proof, I1 would be less than or equal to the term that we wanted to. Less than or equal to summation j in j, 1 over n plus 1 times p. P here is just mu a in j. Right? And then we had a mu a in j here. So they magically cancel each other out. So what I get is how many j's there are divided by n plus 1. And there's a 2 as well. Okay. So that's the part that controls the variance. So that you can see the variance, if you go back, there's this extra piece here. So this variance term, basically expectation, what we showed. So putting the pieces together, we get expectation I from 1 to n wi squared x is bounded by 2j n plus 1 plus probability of b, or x not in b, or in b complement. Okay, because like all the distributions on RD are tight, so I can just take this big enough so that this is less than epsilon for any epsilon that I want. Right, I can make it small enough by taking b big enough. And this one is by assumption. So if you look at the assumption, this is exactly, so the cardinality of this is, I believe this is what I call j here. Okay, so what this is saying is j over n is going to 0. Okay, that's the assumption that we have. The number of partitions that intersect with b divided by n goes to 0. By assumption, this is going to 0 as n goes to infinity. So by assumption. And this part I can make as small as I want because epsilon is arbitrary. I can conclude that as n goes to infinity, this goes to 0. Okay. It was a little bit tricky, but you can see in the end, you're like controlling the expectation of an inverse of a binomial, which is what you'd expect for the variance to, like, basically you have the count how many points there are, and 1 over basically how many points there are. But yeah, what we did was yeah, I would say go through this argument. So this step basically just a discretization. So x could vary in b. What we did was just discretize, say, whenever it is here or here or here, we do this separately. So you basically So this bound is not bad. So because these partitions are disjoint, right? Assuming that they're disjoint, which we assume. The only thing that you're paying extra here are the parts that are not part of this B. So if the partition is like cubic, and you take B to be exactly a cubic set, then these two almost are equal. Okay, so there's no, basically we decompose an event into disjoint events. Okay, instead of, so that's the tricky part to deal with the randomness in X. Okay, so basically you discretize X. So X is like has a general distribution. You said, let's discretize it. Just consider all the mass that is there and there and there, and then each one is a binomial distribution. And it's an interesting sort of way of proving things. Might not be obvious. It was a little tricky, but basically discretize the distribution of X over these partition cells, and then control the expectation in each cell. And in each cell is basically, this is like a similar idea. Once you do this, it's like the warm-up example that we did, as if the X is like has discrete supports, right? So you can imagine that X just takes values at the center of these if you want. Okay, so the partitioning sort of allows you to sort of discretize. So the partition cells are enough, small enough, let's say, or that the number are big enough. So if you really think about this, this is just a simple, like not simple, but like natural extension of the simple example that we did. Instead of having fixed support points, you just discretize and treat each cube or each of these as a new value for X. So over this, I'm going to assume that I have, or I care about how many points there are. So as far as the variance is concerned, you don't care about the actual value. Just what value you assign to the function doesn't matter as much as how many points there are. Okay, so that's how you control the variance. That's true. So that takes care of the variance condition. The other condition is really simple. Still have to cheat. Okay. So what I want to do, like the locality condition. So there is a middle condition that the sum of the weights goes to 1 that you would do as a homework exercise. It's really simple because almost always it's 1, except the case where the cells are empty. And you can imagine with high probability, they're not going to be empty. So it's a really easy proof. So exercise, show that summation, this goes to 1, and probability as n goes to infinity. This is easy. Now show locality, which is, if you recall, I from 1 to n, there was absolute value, so I'm going to drop it because these are non-negative. And then xi minus x bigger than a, I want this to go to 0. So the weights of the points, the weights that they assign to a point I, if point I is far from x, the summation of those weights has to go to 0. So here what we do is we're going to use that J, the set that we had. Where did I define J? So that's the J. Just all the partitions that intersect with B. Again, we have a B there as well. So fix B. In this case, actually, it doesn't matter though. What I'm going to do is I'm going to, so if you recall the condition, the diameter of these is going to 0 over this J, the set. So I take n big enough so that the diameter is sufficiently small. Okay, so the partitions are getting more refined. So if you get big n, so the partition depends like the sizes of the cells depend on n. That's what you have to do. So I'm going to take n large enough. so that diameter of A and J is less than, let's say, A for all J in that capital J. Okay. Then I'm going to say, assume X is in B. Then xi minus x bigger than A, what does this imply? So this is saying that xi, if I put a ball of radius A around X, so if I have X, put a ball of radius A around X, this condition says that xi is outside this ball, right? And I know the diameter of these sets is less than A. And I know that the cell that contains X is one of these, right? So there is a cell that contains X. It has to be in this ball. So let's say the cell is this. This is A and X. A and X has to be in this ball because the diameter, this A and X is one of these, and the diameter of all of these is less than A. So this is there, and xi is outside the ball. So then what is the conclusion? Sorry? Yeah, great. Yeah, so basically xi does not depend on that, that does not belong to that cell that X is in. Okay. So what happens so what is the weight that I assign to xi then? If 0, yeah, so what this is saying is, it's just partitioning is extremely local. So already, if you can imagine, the weights are not going to 0, the weight exactly 0. So if X is in B and xi(x), then this event is a subset of this event. And this is a subset of the fact that, this means that implies that Wix is 0. Okay. So we just have to just put this back together. This is, let's call this Zi. So what I'm having here is, I want the expectation of the summation of Zi's, I from 1 to n. Okay, I'm going to again do the trick. I from 1 to n, Zi indicator x in B plus Zi indicator, say, like this. Indicator x in B, summation Zi, I from 1 to n, plus indicator x not in B, summation Zi, I from 1 to n. So I get expectation, summation Zi, x in B, plus here I'm going to bound by probability of x in B complements, because the summation of Zi is bounded by, so the summation of Zi is bounded by the summation of Wi's, which is bounded by 1, because this is either 0 or 1. So I have this, and what do we conclude about the Zi indicator xp? So so this is saying if x is in xb, Zi also has this indicator, right? So x is in B, and xi minus x is bigger than A, so then Wi has to be 0. So this thing is just 0. And there's no need to do expectation. Okay, so I get just the probability that x is in. complement, which I can make it less than epsilon for any epsilon I want. So again, just conceptually, it's very simple because I can make, this is saying the weights of the points that, the sum of the weights of the points that are outside a ball of radius A around X has to go to 0, right? So what it's saying is that if I have, just intuitively, I have X here, what it's saying is that if I put a ball of radius A for any A, all the other like training points that are outside this ball, the weights, the sum of the weights has to go to 0. But what happens is that I can, for any A, I can make n big enough such that the partition cell for this is inside there, right? Then all the points that are outside here are not in this cell, so automatically get the weight 0. So the sum of the weights is definitely 0. Just the bounding is just a nuisance. I mean, for this part, you don't need to bound. If you, for example, assume, this is from the book, Distribution-free regression. So they assume this is a weaker condition, but you can just assume that the maximum diameter for all the cells is going to 0. So you don't have to like deal with the B here. The B we need for this because you want to count, and we can't count the entire sort of partition because they're infinite cells usually, unless things are bounded. But conceptually, it's very simple. So the locality is immediate. Okay? The only thing that you really need to convince yourself is the variance, and it's also sort of clear. It's just a little bit tricky. Okay, again, the locality follows because for any radius, my partition cells are like dependent on the training, the n sample size. I let n go to infinity, and my assumption the diameter is going to 0. So at some point, this is going to be entirely in A. So all the things that are outside A, all the training points contribute 0 weight. And so the sum of the weights is 0. So that condition is automatically satisfied. You could have just said this without like worrying about the, maybe next time I teach, I just say this, avoid writing it down. This is just a formal argument, right? Sounds good. So we have a proof. The interesting thing is this is a very simple estimator, and there's no assumption that these are cubic cells. So you could have very like complicated. It's like they could be Voronoi cells, or they could be, for example, if you think of the neural networks, if you have ReLU neural networks, if you think of the domain, they're piecewise linear on cells. Okay, so they're like other neural networks where the nonlinearity is a threshold function. They're called linear thresholded functions or linear threshold functions. We may or may not see in this course depending on how far we go. So for those where you have a neural net, so you have a linear function and then you threshold, and then another layer is like another linear function threshold. The level sets of those are so those are basically, you can think of them as the piecewise constant on cells. So they look like they look like this, but the weights are sort of not uniform. So they're piecewise constant, but the way that you weigh the data points is different. Okay, so it's like a data-dependent partitioning estimator, at least the threshold of neural. And then you train, so you learn how to weight the data. So it's a more, I would say, more sophisticated partitioning estimator. Sounds good. And then for the cubic case, we did the calculation last time. The conditions are the diameter goes to 0 means the side length of the cubes goes to 0, and then this condition has to be, because you can imagine the volume of these like grows like or scales with h to the d. So the number is basically how many you have. It's like h n to the d. That's like how many cubes you get in a bounded set, roughly. and then you divide it by n, this has to go to 0. So this condition. So there is a very large gap, a lot of bandwidth to satisfy this. And in practice, the question is, what is, not bandwidth, just side length. What is the optimal side length? That's the thing that you have to worry about. So this kind of consistency results are like a soft theorem. They tell you that you converge to 0. How fast you converge, how exactly do I need to set this? It doesn't tell you, and it depends on the class of functions. Okay, so if you want to be very general, you might not be able to say much. So there might be functions for which this has to go very slowly. There might be functions for which this could go much faster. Has to go fast, like slow is better, sort of. Or I don't know. So there's like the bias variance trade-off. We'll see an example at least. Maybe not today, but next time. We'll do rates for k and n, and you can see how you can set the optimal threshold if you assume some more regularity for the class of functions. So questions? So let's do the k and n. K and n's are also universally consistent. So k and n would be something like this. So what I'm doing here is I'm using this notation. If you look at the training data is x1, y1 up to xn, yn. So what I need to do is, for any data point x, I have to find the k nearest neighbors. What I'm saying is that this notation is the ith nearest neighbor to little x according to the x coordinate. Okay, so I order the data points, like both coordinates, but I just order them by how far or how close to the little x they are in the first coordinate. Does that make sense? So if this is x, let's say this is x1, y1, this is x2, y2, this is x3, y3. Okay, x1, y1 would be just x3, y3. Okay, x2, y2 would be x1, y1, because this has the closest x coordinate. So this is has the closest x coordinate. This pair goes first. This has the second closest. This is the next, and then x3. Y3 is just x2, y2. Okay. It's hard to write down the KNN, the formula, but this, if you agree with this notation, then you can write KNN like this. So it's just 1 over k summation I from 1 to k. The y coordinate of these, the first ith data point. So it's like an ordering, but ordering according to x. So KNN is going to be consistent, like the KNN regression estimator. If k goes to infinity and k over n goes to 0, this is again for variance control. This is, I believe, for bias control. We'll see. So intuitively, if k is, so there's some images here. So this is for like k equal 5 in the univariate case. So this is the prediction, like not the prediction, it's actually the estimate of the function. Basically, for each point, you average over the first, at the top, in the closest k. And as you increase k equal to 10, you can see the wiggles go slower, and this is k equal to 50. Right? It gets smoother, and k equal 100. So you can see k goes to infinity, the variance sort of comes down, but you also introduce the bias. If I increase k, eventually this gets very flat. Okay, so if this is varying very, very wildly, then I lose that. So it's very easy to convince yourself that the bias variance sort of trade-off is according to k. So if k gets bigger, the variance goes down, the bias generally goes up. Okay, and this is like there is an optimal k. This is for the expected MSE. Basically, what I'm trying to plot here is this thing that we are trying to bound. So there are two ways that you can do this. You can either take the expectation only under the test for the particular training set that you have. This is what you want in practice because you don't get many training sets. What I'm plotting here is taking the expectation both on the test and on the training. So this is going to be deterministic. So this is the average behavior for the function that I have. So I have a fixed function, f star, but I'm averaging over all possible trainings, like many training points and many test points, basically. And you can see for this one, for example, it's like around here. If you do it, it gets smooth. Like, there's like a flat part here, and it goes very slowly up. So that's so we're going to do some sort of a more refined analysis. Find something that looks like like a finite sample upper bound that looks like this. Okay, but generally speaking, you can see it basically goes to infinity. They can't go to infinity because k is 1, but it sharply drops once you add a little bit, like increase k a little bit. You drop, and then you have fairly like flat region, and it like slowly goes up. Okay, it's an interesting behavior. Okay, so let's try to prove that k and n's are consistent. The first is this lemma, which is saying that if x is in the support of mu is the distribution of x, and if k over n goes to 0, then the kth nearest neighbor to x minus x, the distance converges to 0 in probability. It's an interesting result. It's just saying that if so basically n goes to infinity, but the number of you look at the first k, and then this k is not growing as fast as n. Can you imagine what the situation is? And then if you look at the kth nearest neighbor minus your point, that kth nearest neighbor is going to get closer and closer to x in probability. The proof is quite simple. But let's accept this for now. Okay, see how we can prove this. So for k and n's, if you accept this lemma, if I want to look at the bias, basically, this is the locality assumption. So I want to control this quantity. What this is saying is, so the weights are going to be 1 over k where they're non-zero. So I'm going to put, for k and n, this is always 1 over k. The only complication is that the set for which this is 1 over k is dependent on the training. Okay, what points I weight by 1 over k depends on the training and the x that we're using. But I have this inequality here. So this is saying that so if xi is basically if xi is the ith nearest neighbor where I is less than k, this is going to be 1 over k, and otherwise it's 0. Okay, so if you think about this inequality I have here, if basically the ith data point minus x satisfies this, then I have it in the sum, I get 1 over k here. Otherwise, if the ith data point is like closer to x, then so how can we this is sort of tautology, but can you see it, or should I explain more? So let's say w and I of x is 1 over k yeah, it's hard to write it because okay, if I want to try to write it, maybe let's define Ix to be the set of all data points such that, sorry, the set of all I such that xi is among the k nearest neighbors of x or ox. Okay, so this is the set of the k nearest neighbors of x. If I have ix like that, then the estimator is just summation. It's like size of this is just average over this. And then the size is just 1 over k. So it's just 1 over k summation I in ix yi. Right? So you can think of it as the weights being just ik if I is in ix. These are my weights. Okay. So I can write it like that if you want. So this would be summation I, 1 over k, indicator I in ix, and then indicator xi minus x bigger than a. But you combine these. If I is in ix, then it's one of these. So basically the set xi, I in ix is just x1, x, x2, x, x, k, x. Okay, the set of all the i's that are among the k nearest neighbors are just these guys. So what I would get is basically what I would get is summation 1 over k summation I in ix. You can write it like that. And for I in ix, it's just these xi's are these for I equal 1 to k. Just think a little bit about it. It's just rather quite obvious. It's not something. But then if you agree with this, then I take the expectation of both sides. Expectation goes inside, I get this probability. This probability is exactly what we have here. So this probability is going to 0. And this is an integral. This is the DCT that we talked about. So this goes to 0. Probabilities are always bounded. So this function, as a function of a, as a function of n, so this depends on n. As a function of n goes to 0. And so the integral goes to 0. So the locality assumption is satisfied. The variance assumption is automatically satisfied because you can see the weights are like this. If I square them and sum them, so summation wi squared x is just 1k squared summation I from 1 to n ix, which is just the size of ix divided by k squared, by the size of ix is just k. So there's no funny business because this is not going to be empty. There's just going to be at least one always. So it's just the weights are always 1 over k if I divide by, if you take the square and then sum, you're just summing 1 over k squared k times. So you get 1 over k. And then by assumption, this is going to 0. That's the assumption that we have k goes to infinity. Okay, and then the summation also trivially is going to 1. Actually 1 exactly, doesn't go to 1. The weights sum to 1, they're 1 over k. So the variance is very simple. This is very simple. The only assumption is this locality, which requires the fact that if this condition holds, then the kth nearest neighbor is going to approach when the kth nearest neighbor is close to this, then all the previous ones, like the first, this is the furthest among the k. So all the other ones are close to this as well. So your bias goes to 0. So let's maybe prove this so that we finish this. Next time we have we come back to something more interesting, which is the rate of convergence. How do you prove this? Is it okay so far? I just want to prove this. You can see for the k nearest neighbors, the conditions are very simple. How should I prove this? This is actually almost sure as well, as you will see. The key is like the support here and this assumption k over n. You can see assumption k over n comes here. Let me do it right there. Proof of the lemma. Proof of the lemma. So what I want to prove is, so take x in the support. Supported distribution, it has different definitions, like the smallest closed set such that with probability 1 x belongs to it. Or you can say x belongs to the support equivalently if you put a ball of any positive radius, I put positive mass on that point. So this is saying this is the ball of radius x with radius epsilon. Sorry, the ball of centered at x with radius epsilon. So if this little x is in the support, every ball that I look at it, the measure the distribution assigns to it is positive. Okay, that's sort of intuitive. Otherwise, it's like you can find a ball such that this is 0, it's not part of the support. So this we have, so pick epsilon, so fix epsilon bigger than 0. Put a ball of radius epsilon around x, then this has to be positive because of the fact that you're in the support. Then I'm going to look at the probability. I'm going to show that this goes to 0 in probability. So the kth nearest neighbor of x, there's like an n as well. So if you look at that book's notation, there is an n because this is the kth nearest neighbor among n points and training points. I'm dropping that n for simplicity. So that's why things are going to work in infinity. So this is kth nearest nearest neighbor of x among x1 up to xn. Okay, so n is there as the size. So this minus, and we're going to have x. X is fixed here. So this probability is going to be equal, the event basically is equal to how many points, the number of points that I'm going to assign to, so a ball of radius x. Notation, yeah. So that's the inequality. So this new n is, if you recall, count how many points there are in the ball. So how many points there are in this ball of radius epsilon. So what I'm saying is that if the k nearest neighbor is outside this ball, the number of points that are, like the number of points that are in this ball has to be less than k. Right? Does it make sense? If the k nearest neighbor is here, it means that like less than k are in this ball. Otherwise, this would, any one of them would be the kth one. So these two events are the same. The fact that this is bigger than epsilon is the same as the number of points that training points that are in the ball is less than k. And the rest is sort of law of large numbers. So nu n dx epsilon divided by n. what do you guys think this converges to? This is like the summation I from 1 to n, xi belonging to bx epsilon divided by n. These are IID, like Bernoulli variables. Yeah, so the distribution, like the mu of basically this. Like the expectation of, it converges to the expectation, which is the probability, is just the probability that xi is in the ball. Okay, and this is positive. So now I divide this, both sides of this by n. The rest you can complete for yourself. So this converges to something which is positive. This side is converging to 0 by assumption. Okay, eventually this event will have 0 probability. Sort of, you have to just formally argue it, but the probability of this is the probability of this. This converges in probability actually almost surely because of the strong law of large numbers to 0. So this converges to something positive because we're in the support. This goes to 0 by assumption. So this inequality eventually, like this event is going to be empty eventually, sort of. So this has to go to 0. You can make it formal, but that's basically the idea. It's a very simple argument, but it's an interesting property of k-nearest neighbors. So if the number, if the k is not growing as fast as n, as you get more and more samples, the top k would approach any point. So any point that you fix, you get close to it, and so that's why your bias goes away. Okay, sounds good. So we did sort of weak consistency of partitioning estimators, weak consistency of k and n's. Next time we're gonna come and prove a result. We're gonna like move towards more like quantitative bounds. Next time we're gonna impose some assumptions. So if x is bounded, conditional variance is bounded, and then f is Lipschitz, then you can prove a very nice upper bound. And you can see this is actually the variance, and this is the bias. You can see the bias sort of is k over n. This goes to 0. The bias goes to 0. This goes to infinity. The variance goes to 0, and there's a bias variance trade-off. So there's an optimal value of k that you can choose, and there's an optimal rate. But this requires assumption. So for example, if f star is discontinuous, we still are consistent. So k and n is consistent even if f is discontinuous. But this is like strong, like a smooth assumption. And so this is a general idea that if you impose more conditions, regularity conditions on the thing that you're trying to estimate, then you can get better sort of bounds, better quantities. Okay, sounds good. Okay, thank you guys. See you next time.